Okay, inverse circular functions. So some of the prior knowledge for this will be circular functions, which we spoke about in lecture one, but also some information more from the methods course about one-to-one functions, and also just generally talking about transformations of functions when you start dilating from x and y axes and translating left and right and up and down. Key concepts we'll cover in this will be the inverse sine graph, the inverse cosine graph, the inverse tan graph, and transformations of inverse circular functions. So let's jump into it by thinking about inverse sine graph. If we are to look at, to begin with, our sort of sine graph, we've got in red here, sort of dashed in red here, and in solid line red there as well. First thing we need to recall is that if we need to be able to find the inverse of a function, then the function needs to be one-to-one. So if you can recall, this idea of one-to-one means every x value has a unique y value. And another way to think of it is every output has a unique input, or vice versa. Every input has a unique output. So what we actually need to do with our sine graph in order to be able to find the inverse of the sine graph is we need to restrict it such that it's one-to-one. And that's what we've actually got in sort of solid red line here. So the first thing we're going to say is we're going to actually only be looking at this part, and then it's this part of the graph that we're going to find the inverse of. First thing just to say is that if you do think about your sine graph, hopefully you're aware that at negative pi on 2, negative 1 is sort of the first minimum point, and at pi on 2, 1 over here is the first maximum point. And so restricting it between negative pi on 2 and pi on 2 makes it one-to-one. If we do any more, it will no longer be one-to-one. Now, you're probably thinking, why do we do it there? We could have done it somewhere else. I think it's just convention. We could have restricted the domain somewhere else and made it one-to-one. But this is just conventional, and this is the largest domain you can have such that it's one-to-one. In any case, hopefully you can recall as well that if you want to find an inverse function, essentially what you're doing is you're reflecting it in the line y equals x. So the black dashed line we've got here is the line y equals x. And what we want to do is we want to reflect that red line in that line. So what we do is reflect object in line. So if we click that and then that, we get our inverse sine graph. And what we might do is we might just change the color of that quickly so that it looks a little bit different. So let's make that green. So the green graph now is our inverse sine graph. And remember, what we did was we swapped all the x and the y values. So if we put the endpoints on this inverse sine graph, I think you would agree, what was the point pi on 2, 1 becomes the point 1 pi on 2. And similarly down here, this endpoint is at negative 1, negative pi on 2. So yeah, that is what our inverse sine graph looks like. Sort of goes like this. And a few things we might be interested in is the domain. The domain of the inverse sine graph is negative 1 to positive 1. So it goes between negative 1 and positive 1. And the range, hopefully you can see that the range is from negative pi on 2 to pi on 2, inclusive. So we use square brackets, right? And yeah, that is our inverse sine function. That's what it looks like. Yeah, let's have a look at the inverse cosine function. Again, let's just play the same game. We've got sort of our cosine graph here. We need to restrict it to be one-to-one. So again, just conventionally, one spot we can do the restriction is from 0 across to pi here. And so we actually just going to be taking the inverse of this part of the function, again, because you have to restrict it to be one-to-one. And now hopefully we're aware that, this point here on a cosine graph is at 0, 1, and this point here is at pi negative 1. And so again, what we're going to do is we're going to reflect it in the line y equals x. So what we're going to do, if we go reflect object in line, click that, we get this graph here. And again, let's change the color just so you can tell the difference. So that is the inverse cosine function, which is pretty neat. And similarly, the endpoints will swap as well. So the point that was pi negative 1 becomes That's not right. One second. Yeah, so just fix that up there. The point that was at pi -1 is now at -1 pi. So that's that point over here. And similarly, this point here that was at 0, 1 is now going to be at 1, 0. So that's there. And yeah, you can see that these lines are reflected in the line y equals x. And so yeah, obviously the line in pink is our cosine inverse function. And the domain, hopefully you can see, is from -1 to +1. So that's there to there, right? And now let's think about the range. The range is from 0, the minimum y value, to all the way up to pi. So 0 to pi is our range there. And that's the inverse cosine function. Let's have a look at the inverse tan function. Again, has to be 1 to 1, but the tan graph, nicely enough, is 1 to 1 between its first set of asymptotes. So hopefully you can recall this is the tan graph. And what we're going to do is we're just going to take that and we're going to reflect it in the line y equals x. So if we do that, we get something like this. And again, let's just change the color. So we get that. And yeah, what we can do is we can think about where the asymptotes were and then sort of how those change as well. So originally, for our tan graph, we have asymptotes between -pi/2 and pi/2. And again, think back to your unit circle. Tan is undefined at pi/2 and 3 pi/2 and at -pi/2. So this is sort of our asymptotes, vertical asymptotes. But those vertical asymptotes will become horizontal asymptotes when we take the inverse of the function, as you can see. So it now becomes like this. And yeah, what we can do is we can talk about the domain. I think you would agree the domain, so remember thinking left to right, the domain of the inverse function is the domain of this sort of brown line, which is all real numbers. There's no real number there that we cannot get. And the range, however, is from -pi/2, which is this horizontal asymptote now, up to +pi/2, which is this one here. And hopefully you picked up the error. This should be not including, shouldn't it? Yes, so we need round brackets here because we cannot include pi/2 and -pi/2 because it never gets there. It gets closer and closer and closer, but never quite gets there. So that is the inverse tangent function. All right, let's have a look at transformations of inverse circular functions. What we're going to do here is we've just got the graph sine inverse of x just from before. It looks the same as this green one. And what we want to do is we want to start to do these transformations. So now the general form is a multiplied by sine inverse of n multiplied by x minus h plus k. So let's just think about what each thing does. Hopefully you've seen this before. If we change a, it's a dilation by a factor of a from the x-axis. X-axis this way, we're going from the x-axis, so it goes like that. If a is between 0 and 1, sort of compresses it. If it's less than 1, it's going to be a reflection in the x-axis. It's going to look like that. Okay, so that is what A does. That's what this A out the front does. Let's look at this N. This N, the way we would say it is, it's a dilation by a factor of 1 on N from the y-axis. So if we make that larger, we'd say it's a dilation of 1/2 from the y-axis. So it's squishing it this way. Similarly, if it's sort of between 0 and 1, we would say that this is a dilation of 2 from the y-axis because it's 1 divided by 0.5, which is 2. Similarly, if n is negative, it's going to reflect it in the y-axis. Okay, so let's put that back to 1. Okay, h. If h is positive, it moves it to the right. Okay, if h is negative, moves it to the left. Okay, so let's maybe move it to there, move it to the right by 1, and then k moves it up and down. So it's our vertical translation. So k goes down, so that's maybe there now. And then if we move it up, it goes like that. So that is all of our transformations of inverse circular functions. I hope you would agree that you could do very similar logic with cosine and tan as well. You're pretty much doing the same thing. Again, A is a dilation by a factor of A from the x-axis, N is a dilation by a factor of 1 on N from the y-axis, H moves it left and right, K moves it up and down. So hopefully you found that useful. As always, if you're finding these videos helpful at all, please consider giving it a thumbs up or subscribing so that we can get the word out to as many people as possible. And yeah, let me know how you're getting on, and I'll talk to you soon.